Today's video is about kinetic energy, work, and LOL diagrams. As you may already be aware of, there are two main types of energy, kinetic and potential. Energy within a system is always conserved, which means that it can neither be created nor destroyed. However, it can be transferred to other objects outside of the system, and we will learn more about that later. For right now, we are going to be focusing on kinetic energy. Kinetic energy is the energy of objects or systems in motion, and our equation for kinetic energy is Ke equals 1/2 times the mass of whatever object or system we're studying times the velocity squared of whatever mass or whatever that we're studying. Now let's put this formula to work using an example problem. Example problem number 1. What is the kinetic energy of a 5 kilogram object sliding on a frictionless surface at a constant speed of 4 meters per second? We know that our equation for kinetic energy is Ke equals 1/2 times m times v squared. That's supposed to be a little separate. Oops. Okay, so we know that our mass is equal to 5 kilograms and our velocity is equal to 4 meters per second. So once we simplify, once we simplify this equation, we get that kinetic energy is equal to 2.5 times 16 joules. By the way, this joules is the unit of energy, and you're going to use that no matter what kind of energy you're dealing with, whether it's kinetic or potential or whatever. Which means that we get our kinetic energy in this situation is equal to 40 joules. There we go, that's good enough. Now let's try another example problem. Imagine that we had a 10 kilogram object sitting at rest on a frictionless surface when all of a sudden we come along and push it so that it starts moving at 5 meters per second. How could we represent this situation graphically? Because in our other example problem, we only dealt with one instant of kinetic energy, but in this situation we have two. We have the before, which is when the box was just sitting by itself undisturbed, and then we have the after, when the box is moving, and we can already see that up there. So, how can we represent this situation? I am glad you asked, because we have a great tool for that called LOL diagrams. LOL diagrams are a great way to analyze situations with changing amounts or distribution of energy in a system. So, this is how they work. You are going to draw out an L, an O, and an L. It's a shocker, right? Obviously, you probably want these to be a little bit more straight, but it's not the end of the world if they're not. So, what each of these is going to represent is the first L is going to represent the initial energy distribution of your system. The second L is going to represent the final energy distribution of your system. And the O is going to include whatever system you're using. And I'll show you again an example once we go back. So for your L's, you're going to want to label the axes with kinetic energy and potential energy. There are different types of potential energy. We'll get to those later. For today, we're only going to be concerned with the kinetic energy, but I'm going to show you how to label this just in case once you get to that point. So we have potential energy of gravity, potential energy spring, and potential energy internal. And you are going to want to do the same thing on your other L, and obviously you can just write maybe G or SP or whatever you want to do. It's not really that big of a deal. Okay. Now to show you how LOL diagrams work, let's go back to our previous problem and draw out our LOL diagram. So we have our big L, our O, and our other L. And again, this is our initial, our final, and our system. So our system in this problem is just going to be the box for right now. And eventually you are going to deal with more complicated systems, but for right now, let's just start simple. And we're only going to be dealing with the kinetic energy of this box, so I'm just going to label kinetic energy on each of my axes and not worry about the potential for right now. So, in our before picture, our box is not moving, which means it has absolutely no kinetic energy. It could not possibly have any kinetic energy. But, in our after picture, our box is moving, which means we have to calculate our kinetic energy. So, as we already said earlier, kinetic energy is equal to 1/2 mv squared, which in this case is equal to 1/2 times 10 times, that's supposed to be a 5. Let's scribble that out. 5 squared, which means that it's equal to 125 joules. Now, let's record that on our final. I tend to use only one box. Some people like to split their bars up into smaller boxes. Either way you like to do it, it's fine. Basically, the boxes are just meant to be a mental indicator of where the energy is lying. It's not quantitative, it's more qualitative. So, for example, they really don't have to be to scale, this is just to help you picture the distribution of energy in the system. So, we have 125 joules of energy, of kinetic energy rather, in the box system after we pushed it. But you might be saying to yourself, didn't we just say earlier that energy within a system is always conserved? How on earth did we manage to have a difference of 125 joules? What happened? Something must have happened to create that difference, right? And the answer, is yes. This change in energy is something that is known as work. Work is the change in energy of a system that occurs when a force causes a displacement in the system it is acting upon. I know that sounds like a bunch of Greek, but for today we're only going to be focusing on this beginning part. Work is the change in energy of a system. Now, if we look back at our example problem, we can see that our energy changed from beginning to end. In the beginning, we had 0 joules of kinetic energy, and in the end, we had 125 joules of kinetic energy. This means that there was 125 joules of work acting on the system. And this came from our push. So we acted on the system. This should be a positive 125. We acted on the system to give it those extra 125 joules. And so we can see that a system can either gain or lose energy by acting on or being acted upon by other systems. A positive number for work means that the system is being acted upon and is gaining energy, whereas a negative number for work means that the system is acting on another system and is losing energy. Let's work on one last problem. A 3-kilogram skateboard is traveling positive 4 meters per second when it hits a speed bump, which applies negative 10 joules of work to it. What is the skateboard's velocity after the bump? Let's use our LOL diagrams for this problem. Here's our L, O, and RL. And we're also going to be dealing just with kinetic energy. I apologize for my askew axis, but you know, stuff happens. So, let's first calculate our initial kinetic energy. Our mass is 3 kilograms and our velocity is 4 meters per second. So, our kinetic energy initial is equal to 1/2 times 3 times 4 squared, which comes out to be 24 joules. So let's go back to our LOL diagram and let's write down that we have 24 joules of kinetic energy in the beginning. And I forgot to define our system earlier, but our system is the skateboard. In the problem, it tells us that the speed bump is applying -10 joules of work on the skateboard, but we could also visualize this as taking out +10 joules from the skateboard. So this is an or situation, not both, so don't go taking out 20 joules from the system, just 10. This is just an alternative way to visualize it. So, in order to find our kinetic energy, final, we are going to have to add up or subtract, depending on your definition or interpretation. The final kinetic energy is equal to the initial kinetic energy plus any work that we may have had. So, in our case, our final kinetic energy is equal to 24 joules minus 10 joules, which means that our final kinetic energy is equal to 14 joules. So we're going to write that right here in our little final kinetic energy, 14 joules. And now we can use this in order to figure out the skateboard's velocity. So if our kinetic energy is equal to 1/2 mv squared, and we know that our kinetic energy is 14 joules, and our mass is, I believe it was 3 kilograms, yes, 3 kilograms. We can use this in order to figure out our velocity. And I did not intend for this to happen, but this is going to be a very ugly number. It's going to be 28/3 is equal to v squared. So the square root of 28/3 meters per second is equal to the velocity. And I'm not going to work that out because it's going to be an ugly number anyway. But the important part is this process. So thank you for watching this video. I hope you found it informative, and I'll see you next time.